All right, so the plan is that this lesson will occupy 2 days of instruction. That isn't necessarily true. So we'll see how fast we move and how much time we need for this. And then we might modify what your homework assignment is. But for right now, plan on having 2 days to complete this. Looking at what we need to do and time we have to do it in, we need, it would appear, we need 22 days of class together. Right? We have that many, and we have slightly over that. So hopefully, hypothetically, we will have time for some projects at the end of the year, like I do an egg drop project where you have to design egg protection modules, and then I go up on the roof and I throw them off the roof. Whatever we have time to get to, I've got projects like that we would do. So, all of that to say, if we don't need to take 2 days to do this lesson, we would rather move faster than slower so that we have more time at the end of the year to do that cool stuff. So, let's dive in. So, let's say, instead of reading the first paragraph, I'm going to go down the rabbit hole of when I eventually lose my mind. So, when I eventually lose my mind, I come back to you guys and I say, I can't remember math. Right? The first thing my mind gets rid of is math. So I say, I can't remember. I know there's an easier way to do this, but I went to the store and I bought eggs. I bought a dozen and another dozen, another dozen, another dozen, another dozen, another dozen, one more dozen, and another dozen after that. I can't remember the easier way to say all those dozens that I bought. No. That's where you just looking at the book and assuming that's the word I'm getting at. Well, not always safe. Whatever it is. So I said I bought a dozen and another dozen on top of that, one more dozen and on top of that, one last dozen. 4 dozen you got. A dozen of a dozen. So wait, what I said, so Savannah's saying what I just said to you is adding a bunch of dozens. The easier way to talk about it, but what math is that? That's multiplication. Now, what if I then, okay, yeah, multiplication. So, what happens if I have 5 times 5 times 5, another 5, and then for good measure, one more 5, all multiplied together? So, exponents, or powers. This is the first thing you need to write down about this. An exponent is just used to represent repeated multiplication. And that's where scientific notation comes in. Scientific notation just takes your information of powers and makes it specific to tens. So scientific notation is just exponents on tens. The reason we do this is we really don't want to say numbers like 0.000000425. Scientists would laugh at each other, and most scientists don't laugh at each other. They're very like the Big Bang Theory is probably not a good representation of scientists. Most scientists are pretty ugly. Let's be efficient. I'm sure they have a good time, but when we're talking about the science, don't waste your time telling me 15 zeros if we could create a math system to more easily and more quickly represent that number. Or if we're talking about the distance between here and Mars, rest in peace Mars rover, if we're talking about that, we wouldn't want to talk about it in straight up miles because it's a lot. So we'll use scientific notation and say, oh, it's 3.4 times 10 to the 17th or something like that because it's fast. what it really means is like 3 quadrillion miles, but we can say it more easily. So, all of that for your intro, let's dive in. So, this is the most common mistake. 3 with a power of 5, I'm not even going to ask the question, does not mean 3 times 5. Now, you're all smart people. I think you know 3 times 5 is 3 times 5, and that would come out to be 15. But 3 with the little 5, just to make sure we're all comfortable and have it on our paper, means 3 times 3 times 3 times 3 times 3. Which already saying it only 5 times should be annoying to you.
3 times 3 times 3 times 3 times.
Are you trying to just get more and more horizontal and keep talking out of turn, or are you with me writing notes? Because the only way I'm going to let you sit in those desks is if you actually sit up like a student and you act like you're in math class. You're going to act like you're lounging at the movie theater, just go to the office. I don't need it. I love you, dude. You're awesome. But all I've watched you do this whole class is get more horizontal and just keep talking out of turn. So, we're going to try our hand at this table. And because we're the accelerated class, I want to see how many of these you can effectively do on your own and get all the way to complete simplified form. So we're going to do one together and talk about the one that they have. If you were given 5 squared times 5 to the 5th, which are situations that you will encounter, well, really, we know 5 squared is 5 times 5, and 5 to the 5th is 5 times 3, you know. So really, we have 7 5s there. We can simplify what we have written by 5 to the 7th power. Likewise, if we have, which one should I help you with? Let's do this one. If we have 7 squared, that's really 7 times, actually, sorry, go ahead and write this down on your paper. We'll make that the first one that we do. You don't have to have your table in order. Just write that down first. And then let's put an equal sign, just so we're comfortable with what we're doing. That 7 squared is 7 times 7. That x cubed, x times x times x. That 7 is just a 7. That x squared is x times x. So when I clean it all up, and I apply that commutative property of multiplication to move things where they fit better, how many 7s do we have in total? 3. So we have 7 to the 3rd times x to the 5th. We're doing that with all of these. Some will be real quick. Some will take a little bit more thinking. Give it a shot.
Good morning, Quinn Wilson. Please come to the office. Quinn Wilson, please come to the office. Thank you.
Oh. We'll tell them, I love how they try to talk to you and their fingers are looking in your mouth. Why are you asking me a question?
What school do you go to?
Yeah, my dentist is like trying to have a conversation. I'm like, dude, you are in my mouth. I like talking while I get my hair cut. You just gotta make sure the hair doesn't go in your mouth. Go ahead and have a good one, man. So, from here, we're going to start to kind of try to formalize some rules that we could say. So, we have an exponent number times an exponent number that both have the same base, because the base is the number, then we have the exponent. Right, so the base is the thing with the exponent. What could you say we do with the 2 and the 4 from like the second situation up here? We are multiplying the numbers, but what do we do with the exponents, Mallory? So this is where exponent work starts to become confusing for some kids. We are being told to multiply. However, what we're talking about with the exponent is how many we have all together. So we then need to add the exponents. When the numbers multiply, we add the exponents. So 3 to the 7th times 3 to the 2nd would come out to simplify to 3 to the 9th. X to the 3rd times x to the 5th simplifies to x to the 8th. This is also why I thought this might not need 2 days. We're all bright. We pick up on things quickly. X to the 3rd, y to the 2nd, xy squared. Connor?
X to the 5th times y to the 4th.
Ooh, I'll agree with y to the 4th. Now, how many x's do we have in the first one? 3, right? X times x times x. And then times x. If there's no that square only goes with the y. So if there's no power shown, what power is there? 1. Yeah, it's x to the 4th. Be careful, not 4x, but x to the 4th. If a power is not shown, it's 1. Right? Because x, there's just one x. It's x times nothing, but it's x. There's just one x hanging out by itself. X squared, x times x. X cubed, x, x, x. So in the last one, if I just go through and I pick terms one at a time, we know that we like to write the constants first. Braylon, you want to talk me through it?
So 2 times x to the 4th. The exponent 2 only goes to the y in the last
Yeah.
So we can do 2 times x to the 5th times 3 times y to the 2nd.
Ooh, we can put the 2 and the 3 together also. Yeah. So I like what you said, but the 2 and the 3 can multiply with each other. Because remember, commutative property, I can move things around. So we get 6 x to the 5th y squared. Any questions on that entire table? Now, we are totally shifting gears from what we did in this last chapter. Like, now we're kind of back on some pure, like, this is how it works, and we just carry it out. Yeah.
I have one with exponents. Can exponents have exponents?
Mm-hmm.
What?
Mm-hmm.
Can those
Wow.
exponents have exponents?
Mm-hmm. So that, I will give you the answer that is the blanket answer that no one, well, not no one, I love this answer. Mathematics allows you to do anything you want as long as you don't break the rules, right? So the anything I want, can I apply a power to something? Yeah. What then happens is the question. So really quickly, just to answer, because I know in your head you might be pondering now, like, wait, how does that work? You do not have to write this down. However, if we wanted to do it, this is really x times x. So x times x cubed, forget about this to the 4th, would be, I gotta get smaller. Three of the x times x, right? 3 of it multiplied all together. So that really comes out to be x to the 6th, which just so happens to be the product. So now we have x to the 6th to the 4th. Can you predict what that might become?
That's pretty math.
That would become x to the 24th. And you don't have to write it all. I'm not writing out 24 x's. So that's now, you don't need to know how to do that yet, but because you asked, I would be remiss if I didn't tell you how it works. So, other things we don't want to write out. If somebody gave you 20 to the 12th times 20 to the 51st, What would you tell them to do instead of writing them all out? Olivia? Add the exponents, right? So when multiplying with the values, we add the exponents. Now wait. Go ahead on your paper. So write that down if you would. 20 to the 12th times 20 to the 51st. And that comes out to be 20 to the
63rd.
20 to the 63rd. So then a teammate walks up to you and they're like, okay, so can I do 10 to the 3rd times 5 to the 4th and just say that it's 50 to the 7th? So, I mean, you said add the exponents, and the 10 and the 5, they have a multiplication between them, right? So we need to put like an asterisk on this rule about adding the exponents. When are we allowed to add the exponents and when can't we? Jessica? What numbers? Only when, what did we say this 20 is? Only when bases match. So you might want to write that down next to this somewhere. The bases are 20 and they match. This does not work. This is not true because the bases do not match. We cannot apply that rule. We can't really apply any rule there. We could do 10 to the 3rd and we could do 5 to the 4th. And then we could multiply them, but we can't apply any shortcut rule. Questions? I cannot capture today because apparently my smart meat got mad at me. So, order of our numbers. Right, 3 times 2 times 3 would be nicer if we could put the 3's together. So if we write it 2 times 3 times 3, is that the same thing? So think about what's 3 times 2 times 3? Well, 3 times 2, then times 3, 18. Okay, what's 2 times 3? Times 3. Oh, yeah. Oh, yeah, because that's that commutative property thing, right? That I can move and it doesn't. Yeah, we remember that, right? So of course we can do that. Yeah. So 2 times 10, right? Same thing as 10 times 2. We remember this, right? We remember this. I need a new job. We remember this. So 2 divided by 10, 10 divided by 2. I mean, division is multiplication, right? So I mean, we can apply the same rules. Why? George? Because you're actually trying to raise your hand?
Because one of them is the divisor and one of them is not divided. I don't know what they're called.
So think about what I said about multiplication versus division, right? If division is the same as multiplication. The same. Peyton?
When you're dividing something, the number you're dividing by, so you're dividing 2 by 10, so you're dividing 2 into 10. But it's not the same because when you divide 10 by 2, then you're dividing 10 by 2, not, you're not dividing the same number.
Yeah, now, I agree. Now, if we want to say division's the same as multiplication, quote unquote, well, kind of. This would really be 2 times what? A tenth, right? So division is only the same as multiplication if we put it in fraction form. Now, can I flip the order and say a tenth of 2? Would that be the same? Yes. So this is just reminder. Commutative property works with addition and multiplication only. If I change it to multiplication, then it will work, but I have to change the physical number I'm using. Like,
is there such thing as like opposite of exponents? So instead of 3 times 3 times 3, it means 3 divided by 3.
well, not quite, but you're close. You're on the right track. Yeah.
Is there another way to do numbers because like addition, subtraction, division, multiplication? Is there another thing that?
Like that goes with powers.
Yeah, but makes a number bigger or smaller, like.
So powers make numbers bigger, right? There is another thing. This is just what Micah was just asking. There's the opposite of an exponent, but we're not there yet. Which, I mean, you might know it, Gabe.
Didn't you just make the number negative?
What do you mean the number?
Like the
Negative exponents.
Yeah, like negative 3.
Ooh, I wonder what would happen if we made it negative. I didn't mean to hit that. Look at part B right there. We have 5 squared times x to the 4th times 5 times x. Go ahead and write this out on your paper, please. I'm going to switch my screen so I have space. Now, who can talk about 5x differently? Like, what's another way that we could say 5x? Somebody said it. 5 times x, right? So 5 squared times x to the 4th times 5. Well, I could really write this 5 times x. And, well, that's multiplication. This is multiplication. I'm going to start to use a phrase that I wish like all math teachers would use. This is a string of multiplications. Which means, like, so there's a term, if you ever go to the casino, of something you're not allowed to do called a string bet. If I'm at a table, and I don't, by the way, because casinos are made to like make you lose, so I don't gamble, I just know about it. If you're at a table and you're gambling and you like look at your cards, and you're like, okay, I'll bet $50. Wait, no, I'll bet. You can't do that. You can't bet something and then say, oh wait, I'll also like, and then you can't. That's called a string bet. Once you make your bet, you cannot add something else onto it. This, and this is why I call it that, is a string of multiplication. And there's actually a ton of multiplication we don't even see here. Because this is actually 5 times 5. This is actually x times x times x times x times 5 times x. It's a string of all this multiplication happening. But all that we care about is does the order of multiplication have to stay how it is? No. So we can pick up, rearrange, move stuff around to make it better. If I put my 5s together, what do I really have? 5 to the 3rd. If I put my x's together, what do I really have? X to the 5th. And that's my simplified exponent form. 5 to the 3rd actually becomes 125. So if I went all the way simplified, it would be 125x cubed. Do that with part C. And I will write up here the original, but clean up part C. I want to see if you can do it in simplified exponent form and then completely simplified form. So if you have a number to a power, try to calculate that. Plus. So get it down to the simplified exponent form, like what we did here, and then like do that multiplication. So this was 5 times 5 times 5, and that gave us 125. We want to do that to have both forms of the final answer. Sorry, I wrote this wrong. My bad. I'm surprised nobody caught this. You lost your opportunity for candy. Find it, find it, find it, find it. This is wrong. That should have been x to the 5th here. The power doesn't change. When I bring it over here, I just did 5 times 5 times 5 and got 125. My brain, I don't know why I accidentally wrote the, but this, please make sure you didn't write the wrong thing on your notes. That should have stayed x to the 5th. That should have stayed x to the 5th. Now, I was wondering why they had the same thing on there twice, and I didn't think hard enough to say like, oh, maybe you made a mistake, Hudson. Thank you, Mallory. I refuse to open my box of Tiger. As soon as I do, they will be gone. I bought cookies from Mallory. By the way, I would normally say first person to get to me for the plant sale gets my order. But the PTSA has asked that we have a community order. But I will break that rule and say if, and this is going to seem unfair, but if you knock on my door at my house as if you were just my neighbor, I will order from your order form. I'm not, so essentially PTSA has told us teachers can't order from kids here, because then whatever kid asks the teachers will get extra order, and it's like not fair. But if you are out in your neighborhood, now, I'm not always home, so you might come to my house and I'm not there and you just miss out. But if you go out to your neighborhood, and guys, your neighbors will buy this stuff. This isn't like magazine sale where it's like, I don't really want a magazine, but people want plants. They want to like have stuff for their garden. This is buzzy. This is easy to sell. Just go put it in front of people and they will order from you. And seriously, they just hand you straight up Amazon gift cards. We told them years ago to quit with the nonsense prizes, like Pokemon cards, and we were like, stop. They just want Amazon cards. Just give the kids a gift card. Yep. So, seriously, how many gift cards they give out will be based on how much money they bring in. But guys, they just walk around the school and they're like, where's so-and-so? I got a $25 Amazon card for them. Yeah, I wish I could do this. Or we've told the PTSA what to give you guys for prizes. That one year they did an iPad for the top prize, but then we were like, a lot of kids have iPads, and if they want one, they can go buy one. Just give them gift cards. So, yeah, Amazon gift cards. It's your opportunity. When I look up here strategically, how many 3s do I have multiplied together? And this is the dangerous thing. It's not how many 3s isn't like how many W's, like 3W. That's not the same as W to the third. Right? Because one is W plus W plus W. One's W times W times W. How many 3s do we have multiplied up here? 4 of them, right? So we have 3 to the 4th. How many W's do we have multiplying? 6. 3, 4, 5, and 6, right? A value without a power has a single power. So then 3 to the 4th, what's 3 times 3? 9 times 3 times 3.
71.
71?
No.
51.
71.
Hold up. 27 times 3. Break it apart. 3 times 20. 60. 3 times 7. 81. W to the 6.
Okay.
You should have both of those forms on your paper. Now, are you ready to change gears?
Yes.
Push in the clutch, find your next gear. You guys should all learn how to drive a stick shift transmission, by the way. In your notes, please write down those 4. Hey, if you would, please write down those 4 things. I'll switch. No, I don't want to switch the screen, so I'm going to write them down too. 9.23 times 10. 9.23 times 10 squared.
Good morning, Gage and Greta Gaines. Please stop by the office. Gage and Greta Gaines, please come to the office. Thank you.
Now, this is one instance where you will sometimes see our multiplication symbol again using the X. And that's why I wanted to write it like that up on the smartboard, is for some reason, a lot of times when people talk about scientific notation, they use the X for their multiplication as opposed to the dot. But sometimes people use the dot because more and more people are catching on to that we've stopped teaching with the X because we use it for algebra. So whichever one you write doesn't matter. The one nice thing is decimal versus multiplication. If I know I'm not doing algebra, if I know I'm not using X as a variable, then you can use it for multiplication. It's all whatever works for you, right? In the long run, please remember, you're doing this for you. You're not really doing it for me. In this moment, sure, whatever, I'm your teacher, but you're doing this for what will work for you. Make your choice. I don't care. Okay, dot x, whatever. 9.23 times 10. I bet we could all do that, and we would end up with 92.3. If we do 9.23 times 10 squared, well, what would 10 squared be? 100. So that'd be 923 with the decimal out here. This would be 9,230 with the decimal out there. So we can make a rule. What could our rule be if we have 9.23 times the power of z? I'm not using x because we have x's up there as multiplication. All we do is move the decimal z places. When we looked at 9.23 times 10, this is 10 to the first. We moved your decimal one place, and that's why it landed here. 10 to the second, we moved your decimal two places, and it landed here. 10 to the third, three places doesn't have space for it. So 1, 2, to move the third place, we have to bring in an extra 0, but we're allowed to do that because it's math. We know we can do whatever we want as long as we follow the rules. Same thing with 10 to the fourth or 10 to the anything, but scroll, come on. You're ruining my suspense. Don't talk to anyone. What would that be?
That is very...
Shh. Shh. I said don't talk. Write it down. Write down your prediction. Write down your prediction. This is like Jeopardy. You can't just talk about it. You got to write it down, and then it's in there. And you got to scribble out the bad answer if you want to change it, because there's no eraser in Jeopardy. Does anyone even watch Jeopardy?
Yeah.
I like it when they've written something down and then they cross it out, and then they write something, and then they cross that out, and they write, look, it's just funny because they can run out of space. Then you have to wager something. And sometimes their wager is like none of it or all of it, or they're like, shoot, I don't know. What would this -5 tell me to do with my decimal? Ready? Nope.
That is...
Octavia?
Like -1 million?
Nope. Why am I brain farting? Olivia's next to me to screw me up. Marley! But what operation could you explain? Sure, yeah, I'll move. That makes sense. Olivia? Divide by 10, 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 which will move it 5 places that way. So wait, I can only move one place with numbers. How many zeros do I need to put out here? 4. So 0.1, 2, 3, 4, 9, 2, 3. So guys, when you are talking about really tiny numbers, you don't want to write out 0.00000 and some numbers. You'd rather just say the numbers you care about and use scientific notation to talk about the nonsense zeros that have to get you there. Because, guys, if you look up what 1 angstrom is, it's like a number, and it uses times 10 to the I forget if it's positive or negative, but to the power of 23. There are 23 decimal place shifts that have to happen to talk about this actual number. Have you been to science yet today?
No.
When you go to science, ask Mr. Kabila what an angstrom is. It's a science thing. An angstrom.
Wait, isn't that weird? That has a weird.
It's got a symbol that represents it. Connor?
Wait, when you're doing like x to the x to the y power and then like m to the b power what do you how do
We
you
haven't done any of that yet.
no but like
You're way too far ahead of us. You got to hang on to that question.
you times the number with exponent different number with a different exponent.
You can only use a variable exponent if you know what the end result is, and then we could solve backwards.
Like when you can get like a large random number from time
So,
another exponent.
So, to tell you where all this is going, I'm going to answer your question, I promise. I know what you're asking. Don't write this down. To tell you where this is all going, last night I was tutoring a student, and they are currently in Math 1, and this is where they're at in their y equals equations. Right? So right now we're dealing with y equals mx plus b. So what this could be used to represent is the population of, let's say, Hoositt Town. Starts at 5,000. If it is growing by 2% every year, that means next year it will be 100% and an extra 2, right? An extra 2%, so 102%. Are we with me? That would be how I'd calculate the population after 1 year of this growth. But if we want to talk about this in big terms and say, well, what about after 20 years of this growth? We'd have to do times 1.02, get the answer, do that times 1.02, get the answer, do that times 1.02, get that, and do that 20 times. I'm out. I'm not doing it. Because instead, we would just say, okay, we're going to do this 20 times. And now we can get the answer like that. Now, if instead they say, in what year will the population reach 20,000? This is where if you have a variable as your x, we could solve this. It's complicated, and you don't need to know how to do this yet. She's in freshman math, 2 years from now. But I'm just showing you where you're going with this knowledge, like why we're doing this. It's to save you time and effort. That's all. It's to make your life easier. Like, no joke, the point of scientific notation is to make your life easier. Like, that's not a me thing, that's a math thing. It's to make life easier. Questions, George?
I don't have a question about this. Are we going into freshman math next year?
Okay, yes, I lied. So next year, yes, but it's math 1. But you'll get there at, like, the end of the year. So this, what would I do with my decimal? Move it 2 places to the right. Here, to move it 5 places to the right, we need to tack on how many zeros? 3 more zeros on the end. We could do all this. We could do all this. At least I hope. This is what we should practice. So, here's the thing with scientific notation. And you should probably write this down. If we want to formalize what scientific notation has to have to be true, this number that we multiply times 10 to whatever power, this number has to be between, let's call this n, it has to be between 1 and 10. It can be 1. Like if you were trying to represent 1 quadra-hundred billion, I don't know, it's like 1 times 10 to the 84. Who knows? But it could be 1. It cannot be 10 because the rule is it has to be a single digit before the decimal. So 1 digit, decimal point, however many digits we need, but this is only ever allowed to have 1 digit in front of the decimal. So this has to become 3.7 times 10 to the something. This has to become 4.871. I cannot make it 48.71. I cannot make it 487.1. It has to be a single digit in front of the decimal. So figure out what powers of 10 would get those numbers. Take a moment. What powers of 10 would get us back to the original numbers? I know, they're early. Easiest way to do this is imagine your decimal where we are going to put it, and then count how many spaces to get back where it actually belongs. So if we put it here, how many spaces to get back? Well, 2, then 3 more, then 3 more, 8. Here, 4.8, well, 1, 3, 3, 3, 10. We'll pick this back up and make sure we're comfortable with this tomorrow, but we'll probably end up going into 822. And I'll give you some homework time to catch up, and I might say, like, omit these problems. Practice this so you're really comfortable. Okay? The homework problems are a good practice set to make sure you go both ways. Take scientific, bring it back to normal. Take normal, take it into scientific. Have a great day, guys. We're not allowed to do that. We would have to do 2 to the 3rd and 5 to the 6th, and then multiply those two numbers together.
No, but when you get like a random number, a number with exponent numbers in it, how do you transform that? How do you transform number to get exponent?
It doesn't always happen cleanly. Like that one may not be able to happen cleanly.
So you can't turn it into a number.